All right, so welcome to midterm one review. So like I said in the email, I'm just going to solve through every single problem now, and then we're going to use Sunday at 6 p.m. in THH 210 and or hybrid to review any questions you have. I realize that the quality is not so good, and that just is due to like the camera and Zoom setup they have in these rooms. So what I'm going to do is at the end of solving each one, I'm going to take a picture of it and then upload that picture, like all the pictures on a document, so you can kind of look back and forth and see what I'm talking about. That being said, I'm gonna like dictate what I'm doing, so at least some capacity should be easy enough to follow along with. Okay, so here we have 2-point charges. We're given both of their charges. They're stuck on the x-axis, and we want to determine the net electric field at that point P, right? So that's E net. So essentially, we need to look at the role of like Q1 on this point P and Q2 on this point P. Right off the bat, though, we remember from that E net equation that's like, KQ over R squared, we need to have that distance between them. With Q1, we have that 6 meters, but with Q2, we need to find what this distance is right here. So I'm going to, we're drawing a line here. I'm going to call it R2, and I'm going to solve for R2. And I'll just do that down here. So sorry, there's like stuff in the way here. So R2 is equal to 6 squared plus 2 squared, right? So 6 squared plus 2 squared. And we're going to find the square root of that. Sorry about the squeaking. Oh my goodness, I hope this doesn't happen next time. So R2 equals 6.32 meters. All right, I'm going to switch chalk now. So it's equal to 6.2 meters. So we have what R2 is equal to. And now we can draw our field vectors, right? Remember that forces in fields always have a direction, right? They're the vectors. And because of that, we can look at the role of Q1 on this point P, positive. So the E field is going to point away. So I'll call that E1. And then here we have a negative charge. So that means the vector is going to go towards it, right? This point the direction of a plus would. So a plus would be, I already broke one chalk. Let's see how many more times I can do that. A plus would be attracted to that negative, and then, with this plus right here, it would be repelled away. Okay, so with forces and fields, we don't write in the negatives, but we let the coordinate system relative to these vector directions tell us their sign is positive or negative. So let's establish a coordinate system. I'm just going to use the standard, the one we've seen a million times here. Okay, and I'm going to have, there's a y component of this E2 pointing down and an x component right here, right? So there's an angle theta between them. So I'll call this E2, and what is it, sine or cosine? It's sine theta, sine theta. Opposite of the angle, it's sine. And inversely, I'll say E2 cosine theta. If it's touching the angle, it's cosine. So I hope you guys can visualize that, but if I looking at the recording, with any like indication, you probably can't. You gotta trust me there. So the x component here going this way is E2 sine theta, and then the y component going downwards is E2 cosine theta. So what's that angle theta? We just gotta use a simple tangent function there. You can see down here. You use a simple tangent function to find that. So I'm going to say theta is equal to, or I'll say tan theta is equal to 2 over 6, and that will lead us to find theta as 18.43 degrees. Okay. So now I basically have everything all set up, and I can work to start solving this equation. So how do we solve for E net? E net, we've now done this so many times in so many different ways, is equal to its x component. So E net, let's call it x squared plus E net y squared. Okay, so let's first solve for E net x. So what's acting in the x direction? Well, we only have one thing. That's that E2 sine theta. It's pointing in the same direction as our x coordinate, so therefore it's positive. If I plug in E2 sine theta. E2 sine theta. I'm going to express E2, so that's K what's the charge that's causing E2? Q2, so Q2 divided by R, which is the distance between them, that's that R2 squared. Okay, we're not done there. We need to add in the sine theta. Okay, so this is a constant. This charge is given. We solve for R2 right here, right? We solve for R2 and we also solve for theta. You have enough to plug everything in. We can solve Enetx as equal to 213.71 newtons per coulomb. Okay, so now we have Enetx. The next thing we need to solve is Enety. So Enety. Let me see how this is looking on the video here. Not terrible, but it looks like someone's like recording through, like a potato. Okay, so we have Enety here. We have E1 pointing upwards in agreement with our positive direction on the coordinate system, and E2 cosine theta going downwards. So that means we have E1 in the positive direction, so plus E1 minus E2 cosine theta. Bam. We have enough to solve this kind of in the same way, right? So I just want to be very clear, right? Forces and fields, we get the sign. Like, how do I know it's negative? It's because it goes against the direction we defined as positive in our coordinate system. That applies to forces and fields. Okay. Where were we? So yeah, E1, we use the same formula we just had, right? So K, what's the charge causing that E1? It's Q1. What's the distance between them? This case, let's call this R1. 6 meters is equal to R1. R1 squared minus E2, K Q2 over R2 squared cosine theta. Again, you have, K is constant. You can factor that out. Q1, Q2 given, R1 given, R2 we solve for, theta we solve for. So then Enet Y is equal to minus 391.3 newtons per coulomb. Bam. All right. So at this point, we have enough to solve for what this Enet is actually equal to. So first, looking at our Enetx. This is positive. Therefore, it agrees with our coordinate system. I'll say Enetx, call that Enetx vector. It's in the positive direction, just like what we defined as positive. Conversely, our Enety came out as negative. Therefore, it's going to go downward against what we defined as positive. So I'll say Enety is going downwards. Enety. All right. We connect these two vectors, like tail to arrowhead from like 135A. And we'll call this Enet. Okay? The angle between them, I don't know, let's call it alpha. And we can now solve for Enet using this Pythag, right? So we'll plug into this equation, that's Enet equals the square root of Enetx squared plus Enety squared. And what you get out is Enet is equal to 445.5 newtons per coulomb. Oh, 0.5 newtons. All right, broke the chalk again. Newtons per coulomb. Okay, but are we done? No, we're not. We still need to, these vectors have a direction. So we have to find that alpha angle. How do we do that? Let's just say tan alpha is equal to Enet Y over Enet X. Okay, you solve for alpha here. Alpha comes out to be equal to 60. Sorry, guys. Let me just erase this. Alpha is equal to 61.36 degrees. And how we're gonna further elaborate on that, it's gonna be below the positive x-axis, right? Because we're just below, this is the positive x-axis, we're below that. Below positive x-axis. So I'll say below plus x-axis. All right, bam. Done. All right, so that's number one. I'll pause the recording and take some pictures. All right, let's proceed with question number 2 here. So here we have 3 charges at the corners of an equilateral triangle, as shown in the figure, and we're given each of the charges. We're looking for the net force on the charge Q1. So I like to think about these ones is looking at the force caused by my charge acting on you. So the way I think about that is like my charge, so Q2 acting on Q1, right? So in this case, I have like Q1, which is negative, and Q2, which is positive. So there's going to be an attractive force between them. But I'm getting ahead of myself. Let's start from the beginning here. So I have my equilateral triangle. Let's start, let's start with the role of Q2 on Q1, right? So it's an attractive force. So therefore, my force vector is going to be pointing towards Q2. I'll call this force 2, right? And then we can look at the effect of Q3 on Q1. So Q3 is a negative, Q1 is a negative, therefore it's going to be repulsive. So there's going to be like a vector coming out this way. I'll call this force force 3. All right. Call that force 3. I hope everyone can see that there. So, we only have the 2 here, right? But obviously we need to break this guy into components. So I'm just going to do my normal coordinate system here. X and Y, like this. All right, and then F2 is completely in the X direction, so we're good there. But this F3 needs to be broken down. So I'm going to have the X component like this, and there's a Y component as such. So there's an angle here, angle theta, and we already talked about it. That means this one's going to be F3 cosine theta. Why is it cosine theta? Because it's touching the angle, and therefore the Y component here is going to be F3 sine theta, because it's opposite of that angle. Now, what's the angle? Well, it's the result of alternate interior angles, right? So if that's theta, that's theta. Frankly, also, this is an equilateral triangle. So if that's theta, because this is theta, and this is theta. What does an triangle's angle need to add up to? 180. 180 divided by 3 is equal to 60. Therefore, theta is equal to 60. Amazing. And then, thinking about this equation, there's that distance r squared at the bottom, and that's just, 2 meters and 2 meters for both of them. We're going to set it up kind of the same way, but now we're dealing with forces and not the electric field, right? This is the electric force. So the equation is slightly different. But we can kind of set up the equation the same way. So I'm going to start by writing over here. I'm going to say F net is equal to F net x squared plus F net y squared. Okay, I'm going to put a square root right here, or same order of business here. I'm going to start with F net x. So F net x. So what's acting in the x direction? Well, we have 2 things. We have F2, which is in, the positive x direction, and we have F3 cosine theta, which is going against what we defined as positive, so therefore it's going to be a minus. So what do we write down? Sorry, it's like, I have to open my notes again. What we write down is F2 minus F3 cosine theta, right? And so F2 minus F3 cosine theta, where we know what theta is already. And F2 is equal to K, my charge, so Q2, acting on your charge, which is Q1, divided by the distance between us squared. Let's call that R squared. And then minus, K, my charge, we're talking about F3 now, so Q3, acting on the position of interest, Q1, divided by R squared again, and then cosine theta. With these questions, it's really important that we factor out, otherwise we're taking a long time. Sorry, helicopter. Oh my God, oh, someone came in to the Zoom. Interesting. All right, I'll finish this and then I'll answer that question. So with this one, I lost my train of thought there. Oh yeah, with these questions, it's very important we factor out, right? Because we don't want to be taking forever typing into the calculator. So what we can do is factor out the K, a Q1, and in this case, both of these R's are the same, so we can also pull out an R squared, right? And that leaves Q2 here minus Q3 cosine theta. All right, so we can now clean up this whole Enetx business, and let me just double check, make sure. Yeah, we're all good. And then we will see is it comes out to be equal to 0.009 newtons, and there's a negative sign here. Okay, so minus 0.009, that's 2 zeros. And the units are newtons, not newtons per coulomb like we would have with electric force. And alternatively, we can now work with this F net Y situation. What's in the Y direction? We only have one force. It's this F3 sine theta, which is pointing straight down. So we can say F net Y is equal to minus F3 sine theta. So minus F3 sine theta. And we just got to say what's F3 equal to? Well, that's equal to K, my charge. Well, it's minus. So it's Q3, Q1 divided by R squared, and then sine theta, where theta is solved for. Q1, Q3 are given, R given, K is constant, the negative sign there. That whole business comes out to be equal to minus 0.047 newtons. Okay, so sorry, I kind of got squished over here, but that leaves us with enough now to solve for what F net truly is. So I'm going to scoot this. Okay, erase this board. Okay, so we're erasing here, and I'm going to say, we already have the equation, right? F net equals square root of F net x squared plus F net y squared. We plug everything in. F net comes out to be equal to 0.048 newtons. And we can draw out the system here. Remember, we have a standard coordinate system. Both of our answers came out negative, so they're both going to be going in the opposite directions of standard. So our x coordinate is going to be pointing, leftwards, and our y coordinate is going to be pointing downwards. We're going to connect them, same order, business as usual. Solve for alpha. Let's call it tan alpha. That's going to be equal to F net y over F net x. Okay, and alpha is equal to 79.15 degrees below, and then we'll call it the minus x axis. Right? So we have our magnitude, we have our direction for forces and fields. Those are necessary because they're vectors. Forces and fields, we use the coordinate system to state whether we're going to be treating something as positive or negative, right? Okay, I'm going to pause the recording and take some pictures. All right, so now we're going to be doing question number 3 here. Kind of same business as question number 1, but perhaps a little bit more complicated. I don't know, it's good practice, I guess. So let's see, here we have 3 charges, at all those corners. We want to determine the electric field at point P, and we'll know the lengths of the side, this one is 0.04 meters, and this one is 0.03 meters. Right? Okay. So we're looking at this point P. So first, what's the field of that Q3 at point P? Well, the vectors will be pointing towards Q3. Why? Because it's negative, right? So the negative, all right, that's the other piece of chalk. So now I'm left with only broken pieces. So the E field will point like a plus would, how a plus charge would behave, right? Although there is actually no plus charge here, but as if there was one. And how would that behave with a negative charge here? It'd be pointing towards. So I'll call that E3. Okay? And that same logic's applied to Q2. That's applied to plus charge. What's the effect of a plus on a plus? It'll be repulsive. So that's why we're gonna have E2 pointing eastward, right? Or towards the right. And lastly, we have Q1. Q1's a negative charge, but it's on a diagonal. So, when we set up our coordinate system, let's do standard coordinate system. It's going to be needed to be broken into components, right? So let's first, draw the diagonal. So it's a negative charge. How is that going to behave? Well, we know it's going to be attractive here. So I'm going to call this E1, right? E1. And it's going to have X and Y components. So I'm going to have a component here, and this component working up to that E1 position, and I'll call that E1, this is the angle theta, sine theta, right? And that means it's E1 cosine theta. Remember, touching the angle theta, therefore it's cosine. Opposite of theta, it's E1 sine theta. Okay? So I'll call this R1. Let's solve for R1. I'll do that over here. So R1 is equal to 0.04 squared plus 0.03 squared. Put that whole thing under a square root right there. R1 is equal to 0.05. All right. And to find that angle theta, we're just going to do, I'll say tan theta is equal to 0.03. Right, so 0.03 over 0.04. 0.04. So theta is equal to 36.9 degrees. All right, 36.9. So next, oh, okay, we're ready to roll. We just solved it the same way we did number one, right? So E net is equal to E net X squared plus E net Y squared. All right, very cool. And then we're going to start with E net X. So E net X is equal to everything in the X direction. So we have an E2 in the positive direction, and we have E1 cosine theta, and that's going against the coordinate system. We define as positive, so therefore it'd be minus E1 cosine theta. So E2 minus E1 cosine theta. All right, am I recording? All right, good. Am I muted? No. One time I did a whole recording muted, so that was fun to do back to back in a row. So that's not happening now. Anyway, same order of business here. K, what's the charge here? Q2. What's the distance? 0.04 squared. And then minus K. Oh, what was this? E1. What's the charge? Q1 divided by what's the distance? 0.05 squared cosine theta. We solve for theta. We plug everything in. We factor out what we can. We clean this guy up, and you can solve for this as minus 0.0013. What are the units? Newtons per coulomb. All right. Next, we move to E net Y. So E net Y. So let's look at what's working in our Y direction here. Well, we only have one thing. Oh, no, sorry, two things. We have E3 pointing upwards. We have E1 sine theta pointing upwards. So they both agree with what we define as positive. So it's going to be an addition between them. So we'll say it's E3 plus E1 sine theta. Okay. So, K Q3 divided by, the distance between them, which is 0.03 squared, plus K, what's the charge, Q1 divided by 0.05 squared. And then now it's just sine theta. All right, and that whole thing comes out to be equal to Oh my goodness, big number. 6250053 newtons per coulomb. Newtons per coulomb. All right. Cool. And now we just solve the same way. Now we have our Enetx, we have our Enety. We plug it into this equation. Square root of Enetx squared plus Enety squared. Square root that whole business. And our Enet comes out to be another big number. 6250053 newtons per coulomb. And obviously, like, it's like very much in the y direction, right? Hugely in the y direction. And because of that, I mean, you can predict, right? So like we have a standard coordinate system, our x direction is negative, so it's like going to the left, and our y is like super positive, so it's like going straight up. And then you can connect them, solve for alpha between, and then alpha is going to be like 90 degrees, right? Because we'll say tan alpha is equal to E net y over E net x. And it's, yeah, so it's like 90 degrees above the minus x axis, because it's like super in the y direction, right? This value is so much smaller compared to this one. Anyway, yeah, you'd say it's 90 degrees over the minus x axis. Okay, so you know we should be kind of comfortable with this. With our second time doing one. All right, I'm gonna take a picture. All right, let's proceed with question number 4 here. So it's a resistivity type question. We have a copper pipe here with an inner diameter given, outer diameter given, and we know how long it is. We want to determine the resistance of the pipe. You know, right off the bat, we're working with areas. For areas of a circle, we need the radius. So just divide those diameters by 2. And that's essentially what I did here, right? Like R2 is equal to that 5 centimeters divided by 2, and R1 is equal to that 4 centimeters divided by 2. Okay. And with this one, we need to recognize that it's a hollow system. So, you know, in our resistivity equation, or the resistance equation, we're going to have, you know, that PL divided by, oh, and you know, this will be given, right? Like you don't need to remember all these specific values, right? Because it's copper, we know that P there is equal to 1.7 times 10 to the minus 8. That'll be given. And we need this area, but remember, it's a hollow system here. So we need to subtract the area of the inner from the outer. So therefore, we can say like the area, like the true area is equal to A2, that's of the outer copper portion, minus A1, that's like the hollow interior, right? And then what's the area? You know, just pi r squared, and we'll say R2, so we're dealing with R2 minus pi R1 squared, right? You're going to work that out, clean that out, and then your area here comes out to be 0.123071. You can now plug that in, right? Oh, I'm sorry. You can plug this in for that area right here. So we'll say this whole thing is equal to that 1.7 times 10 to the minus 8. Again, that would be given times the length. Also given, what was it? As 12 centimeters, so 0.12 meters, and divided by 0.00071. That area we just found, and that resistance value comes out as 0.5027 ohms. Okay, that's what that big R is equal to. Pretty easy one. Just remember that equation and working with the different areas we'll use. Sure, we'll include that business on the formula sheet. Okay, I'll take a picture of this one. All right, so back with question number 5 here. All right, we're good. Back with question number 5 here, Kirchhoff's question. You know it's going to be there, so let's get good at it, right? Look at the size of the chalk I'm using right now. See that? It's horrible. Anyway, yeah, Kirchhoff's, it's going to be on the exam. Like, practices, if there's any bit of confusion, like, let's please talk about this. This is 3 points. Right here, this is easy money, right? So there's two things here. There's a junction rule and a loop rule. What's a junction? A junction is anything where the current has either or option of where it can go, right? So you can imagine like the current's coming up this way, goes up this way, it can either proceed up or proceed right through this system. This is a junction. This is a junction. What about right here, 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 and here? These are not junctions. There's only one way it can go. So I like to label my junctions. We call this A and B, right? So then we all know what I'm talking about. Okay. The next thing I like to do is define the currents. And I've talked about this before during session, but in case you don't come often, I'm going to work with junction A, by the way. In case you missed it, I can almost predict the direction the current will truly be. And what I do is I look at the minus and the plus terminals of the battery. Remember, short side minus, long side plus. Short side minus, long side plus, short side minus, long side plus. And the current realistically will travel from minus to plus. So therefore, I expect within this bottom portion with this 20-volt battery, so that's starting from this B junction going this way up to that A junction, the current, let's call it, let's see, I1 will be going clockwise, right? So clockwise, like going around this way. Because that's the minus terminal, that's the plus terminal. All right, now looking here at this middle section right here. I'm gonna call my current I2 minus and the plus terminal. I imagine the current's gonna be going this way, right? It's gonna be going leftward. Let's call this I2. There, right here, I2. And lastly, look at this 2-volt terminal. I see the minus, I see the plus. I imagine the current's gonna go this way, minus the plus into that B position. So I'm gonna call this I3. All right. First thing, set up the junction rule. So junction, I'm going to call it jump, right? Everything in is equal to what comes out. Every current that is going into the junction equals what's coming out of the junction. Therefore, in respect to this A position, I have I1 pointing into it, I have I2 pointing into it, and I have I3 pointing out of it. I1 plus I2 is equal to I3. All right. And we know that whole thing's equal to 0 when we move things around, but I'll save that for when we clean this whole equation up. Next, we have our loop rules. Maybe I'll do that over here just for to be very. Yeah, I'll do it. To be very clean, so everyone can see what's going on. So. Remember, you can do any combination of loops as long as they both involve like one of the currents, right? So I'm going to do a loop starting with this bottom position here. I'm going to send it clockwise so that it goes through this. So I got to start with a positive 20, right? I like to start with a positive value. So I'm going to set it clockwise. So that's my first loop. Call that loop 1. So loop 1. Loop 1. Remember, delta B, the sum of delta B is equal to 0. Okay, so it's equal to 0. And now I'm going to show you my process of how I do this. Okay, so starting from the battery, the direction of the loop we define is in the same direction as the current I1. Remember, we talked about I1 starts here, goes this way, goes up this way. Our loop is in that same direction, right? You can imagine it. They're both going clockwise. Therefore, positive 20 volts. What's after this 20 battery? It's this 5 ohm resistor. The current and the loop are the same direction. Therefore, it's minus 5 I1, right? So with the battery, it's plus when they're the same direction. But with the resistor, it's minus when they're the same direction. So minus 5, what's the current there? I1. We continue. We continue up. We go up this way. We hit I2. Here, the direction of the current I2 is clashing, right? They're bumping into each other with respect to what we define as the loop. Therefore, plus 3 I2. We continue along. Our loop hits the positive terminal of the battery first. Therefore, it's minus 18. We're going to clean up this expression, and what we're going to have left is 2 over 3 minus 1.67 I1 plus I2. All right, there's a little trick here. So, I did 20 minus 18 is equal to 2. The next thing I did is I divided everything by 3, so I can easily set this whole thing in terms of I2. Like when in the later steps, I can set it in terms of I2. I have I2 just, as the variable. There's no number in front of it. I divided everything by, so I subtracted by 2, divided everything by 3, right? That's why I have 2 over 3, 1.67 I1, and just I2 by itself. Now, loop 2. So I'm going to do another loop here. I'm going to do the outer loop again. And that's because I can already see, like, if I do the outer loop, I'm going to have a plus 20 and a plus 2 if I go clockwise. So that's what I'm going to do. I'm going to go clockwise. I'm going to call this loop 2. Okay? So loop 2, kind of same setup here. Our loop and our battery, the loop goes this way through the minus to the plus terminal, therefore it's plus 20. Plus 20. We continue along, minus 5. What's the current there? I1. We go up, 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 we go right, and then we hit that 2 ohm resistor. There, I3 direction and our loop direction are the same, therefore minus 2 I3. Minus 2 I3. Okay? And then lastly, we hit that that battery. Again, our loop hits the minus terminal through the plus terminal. So therefore it's plus 2. So plus 2. We're going to clean this up, add 2, and then divide everything by 2. So everything will be in terms of I3 when we eventually clean all this up. So I'm going to say this whole thing is equal to 11 minus 2.5 I1 minus I3. Okay, so I have my 2 cleaned up equations, and so it's like this one and this one. I have my 2 cleaned up equations. And if you have a good eye, sorry, I'm getting a bunch of text. I'm gonna go do not disturb. It's distracting. If you have a good eye, you can see that I'm going to solve everything in terms of I1, because I can isolate this equation to equal, I2 is equal to all that business. And for this one, I can just add the I3 to the other side and solve that way. So let's do exactly that. So what I'm going to do is I'm going to subtract everything except for the I2 onto the other side. So I get I2 is equal to 1.67 I1 minus 2 over 3. And then here I'm just going to add I3 to the other side. So I get I3 is equal to 11 minus 2.5 I1. Okay? So now, oh no, don't box that, I'm sorry. I'm just like trying to emphasize that these are our equations we're going to plug in. Now, back to the junction rule. Here, we can solve everything now in terms of I1. So what we're going to do is we're going to move I3 onto the other side. We now know what I2 and I3 are equal to, right? We set those up right here. So we'll say I1 and then plus 1.67 I1 minus, I'll make sure that's a minus I wrote there. Yeah, minus 2 over 3 minus 11 now, right? Because we're plugging it in, there's a negative here, so you distribute that negative. And then plus 2.5 I1, and that whole thing is equal to 0. All right, the equal to 0 on this side. Sorry, I'm running out of room here. Now, I can add up everything with the I1 variable, so I can add 1 plus 1.67 plus 2.5, and I'll get 5.17 I1 is equal to, and I'm gonna, this is like 11 plus or minus 2 point, so minus 11, minus 2 over 3, so that's minus 11.66. Move it to the other side, so it's 11.6, well, 67 round up, right? So it's positive now. Divide both sides by 5.17. I1 is equal to 2.26 amps. All right, I1 band. With I1, we can now find I2 and I3. You plug in that I1 into this equation right here, multiply by 1.67 minus 2 over 3, you get I2. I2 is equal to 3.11 amps. That's I2. Same business. We plug in I1 right here, multiply 2.5 times 2.26, and then 11 minus that value, I3 is equal to 5.35 amps. All right. Now look at the size of the chart. All right. I'll take a picture of this. All right, let's proceed here with question number 6. I think I'm going to need to split this recording up into 2 sections. Otherwise, the recording is going to be too long. So this will close part 1 here. And question 7 and onward will be in the next recording. I'll probably do that tomorrow. Anyway, so this one was pretty tricky. This was on my midterm when I took the class. It's just kind of long, and obviously like the wording is intimidating here. So here we have 4 long straight wires. Tells you what kind of right-hand rule we're going to be using, tells you what kind of equations we're going to be using. So that's like a lot of information there. So we have 4 long straight wires, each perpendicular to the page, are arranged on the corners of a square with each side is 1 meter, right? The wires have those currents and they're going into, out of, and whatever. And we want to determine the net magnetic field, magnitude and direction at the point P, which is at the center of the square. I said squirrel. So 1 meter and 1 meter. We're looking at this point P right here. I'm actually writing it up here, point P. Okay, so we're dealing with a right-hand rule situation. This is going to get messy. What if I should have made that box bigger there? I'll be okay. So I'm going to first draw a coordinate system. I'm just going to do a standard coordinate system. This is going to get wild. It's going to be a lot of writing inside of inside of the square right here. Okay. And just for like neatness sake, I'm going to draw a straight line there so I can kind of figure everything out. And if we remember with this equation, there's an R value, right? Like that's like the distance from the wire to that point of interest. So I'm just going to draw like straight lines to represent each one of those R's for each one of these wires. And we know the R's will all be equal to each other, right? Because it's going to be, you each have to use like, it's going to be half the length, right? It's going to be 0.5 meters. 0.5 meters. We should do pi tag to find R. And all of these equal to R. Right? Remember, that's half of the bottom and then half of the height. You're going to work that out. I'll do that over here. So R is going to be equal to 0.71 meters. That's square root of 0.5 squared plus 0.5 squared. Okay? Now, there's the trick to how I like to solve these. Remember, it's right-hand rule number 2. That's going to be the thumb and curl. So let's start with I1. Okay? So put your thumb in the direction the wire is going. This wire it's dot here, right? So it's coming out of the page. My thumb is pointing out of the blackboard, out of the page. I then trace with my hand to that point P of interest and out curl my fingers. I can see that it's pointing up this angle, up R like this. It needs to be perpendicular. So whatever this line is right here, the vector produced by I1 is perpendicular to that R value. That's equal to 90 degrees. And that has to do with the fact this is a cross product. And I mean, I'm not going to even go down that road. It needs to be perpendicular. The B vector needs to be perpendicular. Therefore, what I'm going to say is B1 is pointing this way. B1 is pointing this way. And we can see this B1 vector is perpendicular to this straight line right here. And it needs to be perpendicular to the shortest distance between these two positions. And that's always going to be the straight line. So perpendicular means 90 degrees, right? So the 90-degree angle between this B1 vector and this length. Sorry, I'm like going on forever about this, but I just want it to be very clear. Next, let's look at I2. X, so I'm going into the page. We go to the position of interest and we curl our finger, we out curl our fingers. Now you can see my fingers are pointing like somewhere in this area, but it needs to be perpendicular to this vector. So wait a minute. I trace it up, fingers curl out, it needs to be perpendicular. See, I like that's perpendicular trick just caught me right there, right? Because I like out curled my fingers and I was pointing downward. I was like, wait a minute, that's not perpendicular. Perpendicular is 90 degrees. So it needs to be going up this way. We'll call that B2. Okay. That perpendicular trick is really helpful. Tell me there needs to be a 90-degree angle between that R, that distance R, and the B vector itself. Let's go to I3. Again, so I'm going into the page, trace to that position of interest, and then I out curl, and I can see, gosh, this is like kind of tough here. All right, so it's kind of like this, right? So that means it's B1 and B3 are pointing in the same direction. So I'll call this B3. Okay? And again, it needs to be perpendicular. That's why it tells me. So that perpendicular trick really helps because it aligns where you're thinking. Because, you know, like with the right-hand rule number one, when we're doing this whole situation, it's very clear like what direction it's facing. But when your fingers curl, it's like kind of hard to know like where is this vector truly pointing, right? So as long as you remember it needs to be perpendicular, the directions will hold true. And then now we look at I4. I4 on this point P, thumb pointing out, we work down towards this position. Okay, we curl, and it needs to be perpendicular. It's pointing up, right? Same direction as B2. So plus B4. So now, again, like it's kind of like awkward, right? To like do this and be like, oh, is it like pointing this way? Is it pointing down this way, like this? Like, what the heck? Like my fingers are curling this way, but clearly B4 is this way. It's perpendicular. There's only two ways it can be when it's perpendicular to this distance R. It can be either pointing up this way or pointing down this way. But because our fingers curl like somewhat in this direction, that tells us it's going to be this way, right? So we can clear that up in person. It's just like, I don't know. I feel like you need to be, for me to really like get this across, like I need to be like, do this and show you in person. But it's perpendicular or however way you want to work with that, right? Now to solve this one, you can do it two ways. You can also readjust your coordinate system. I personally don't like to readjust the coordinate system just because, I mean, with this one, it would be a lot faster to do that, but I don't like to do it just because it kind of throws me off. But feel free to do that if you're comfortable. The kind of key thing to notice here is that we're going to need to find now X and Y coordinate or components, right? So each one of these two vectors is going to have an X and Y component, where we'll call this angle theta, we'll call this angle theta. And right here is B2 sine theta plus B4 sine theta. And then this Y component here is B2 cosine theta plus B4 cosine theta. You know, honestly, in this case, it'd probably be better to rotate coordinate system 45 degrees, but you know, I'll let you guys do that if you want to. And what's theta equal to? I just said it's equal to 45 degrees, and that's just because the opposite over adjacent is they're both equal to 0.05. So I'm sorry, 0.5, so they equal to 1, and 1 is equal to 45. So equal to 45. And then our X and Y components for B1 and B3 are B1 cosine theta plus B3 cosine theta, and then up here, B1 sine theta plus B3 sine theta. So now we have a bunch of coordinates, like the sky's going everywhere. I think it'll be easier to see when I write it all out. So let's start with B net x. I'll do that over, or I mean, so B net is equal to B net x squared plus B net y squared, square root this whole thing. And let's solve for B net x and B net y over here. So B net, let's see what's going in the plus direction, what's going in the negative direction relative to our coordinate system. So we have B2 cosine theta plus B4 cosine theta in the positive x direction minus B1 cosine theta plus, or minus, and we're plugging it in, B3 cosine theta, right? So it's going to be just a lot of plugging in here. So B2 cosine theta plus B4 cosine theta minus B1 cosine theta minus B3 cosine theta. All right. Now we need to express all these things. So I'll write it out all for this one, but for the next one, I'll just skip to the factored form. But that's equal to what's the current I2 divided by 2 pi r. Every single r is the same. Cosine theta, and then plus mu naught I4 divided by 2 pi r cosine theta minus mu naught I1 divided by 2 pi r cosine theta, and then minus mu naught I3 divided by 2 pi r cosine theta. Kind of squished you over there. And we can factor out mu naught 2 pi r cosine theta, leaving in here I2 plus I4 minus I1 minus I3. Plug everything in, clean that whole thing up, and what we're going to get there is minus 0.60 1, 2, 3, 1, 2, 3, 4 t. That's B net x. Now, B net y. Well, everything's in the positive direction, so it's going to be B net y. Oh, sorry, that should be x is equal to B2 cosine theta plus B4. I'm sorry, sine theta. Oh my gosh, I'm running out of steam over here. Sine theta plus B1 sine theta plus B3 sine theta. It's the same thing up here. Just factor this out. What you're just going to have, the only difference is it's going to be the addition of all those currents. So mu naught 2 pi r sine theta, and then that's going to be I2 plus I4 plus I1 plus I3, close parentheses, B net y is equal to 0.00000. That's 5 zeros. 1, 2 t. Okay, so now we know B net y. We know B net x. We can plug it into this equation, solve for B net. B net is equal to, sorry. Handwriting is really small. B net is equal to 0.00001 3 t. Scoot this in a little bit. So 0.13 t. And then you have to solve for the angle of that. And So here we have our x component going the negative direction, something like this, and our y component is going the positive direction, this. So B net is right here. We'll call this theta prime, so tan B net y over B net x is equal, what the heck? So tan theta prime is equal to B net x over B net y. So therefore, theta prime is equal to 71 degrees above the minus x. Okay, above the minus x axis. All right. Sorry, we got a little messy here. So that's part A. Gee whiz. So we found the net magnetic field at point P. Now, in part B here, we're asked, let's see. The wires are so the I2 and I3 are now removed. So the wire, the current I4 and I1 and I4 remain. And we want to determine the force per unit length between the two wires with currents I1 and I4. Give the magnitude and direction, either attractive or repulsive. So, I mean, with a good eye, you know it'll be attractive because they're going, same way right there. So we just solve that using the force per unit length equation. Oh no, need blank. So we can set this up. Let's see here. We have I4 like this, I1 for 2 amps, which is equal to I4, which is equal to 1 amps per meter. Looking for that force per unit length. So we're going to use that equation. B here is equal to the current length cross B, right? And what's the angle between them? Is just 90 degrees, so we don't have to worry about that. So we can divide by length on both sides and say FB divided by L, so that's the variable of interest, is equal to I1 B. All right. And then what's B? That's equal to the field produced by I4. So it'd be I1 and then mu naught I4 divided by 2 pi R, okay, where R is equal to L, which is equal to 1 meter, right? So that's equal to 1 meter right there. We're going to clean this up, and what you'll get is 0. So we'll say like this is in respect to this one position, right? Is going to be equal to, put a little 1 there, so we know we're talking about that one. Equal to 0.6 zeros, 1, 2, 3, 1, 2, 3, 4 meter. And again, like we talked about, it's attractive right there. Okay, and we can find the angle between them. Well, I don't even know if we need to. We certainly need to say attractive, right? All right, attractive. Yeah, I'm not going to even. All right, attractive right there. Okay. Oh, and if you did really want to find the angle between them, it's like 18.4. You'll just have to compare that force vector relative to the V net vector, but we can talk about that in person if you want. But it is attractive, right? Okay. Yeah, that's this one. I'll take a picture of it. Oh, I felt like I just finished writing, and I was like, I feel like I didn't do a good job of explaining why they're attractive. Remember, in lecture, we had those examples when we had 2 wires going in the same direction. In that case, the force between them is attractive, right? So in this case, both wires are coming out of the page, so the force between them is attractive. And you can set up your right-hand rule to prove that. Had this one been going into the page instead of out of the page, it would have been repulsive, right? Both going in the same direction. That's why they're attractive. Let that be the addendum on that. All right, part 1 done.